Yes, sir, you are audible.
Okay. And is my screen visible?
Yes, sir.
Okay. Okay, then let me start. So, yeah, last class we were discussing the Euler-Bernoulli beam element, and then we have discussed some problems, application of that for element. So, we are going to continue with that, a bit more, some more concepts on that. So, Euler-Bernoulli beam finite element. So yeah, no. Now let us say if we want to solve a problem of this type. Let us say I just take an example. Let us say there can be different boundary conditions. Actually, that is immaterial. But I am taking an example that let us say we have this boundary condition. And there can be of course the distributed force, but I'm not showing that. So let us say there is a concentrated force at some point, and also there is a moment these can be there at the same point or they can be at different points. These are externally applied concentrated force and moment. And let us say the distance from the left side is L dash of the point where P is acting, and the distance of point is L double dash where M is acting, and maybe the total length of the beam is let us say L. So now for solving this problem, now we have a concentrated force no at these two locations. And so now one way is that we discretize this beam actually into three elements. So one element would be, let us say this is location A, and this is point B, this is point C, and then this is D. So we take one element from A to B, another element from B to C, and then third element from C to D. So one possibility is that we discretize the whole beam into three elements, and therefore we have a node at each point, a node at a location where concentrated force or moment is acting. So then we know how to write the internal forces in the assembly in terms of these external forces. So that is one way of solving this problem. The other is, although we usually prefer the first, the way I have just told, but there is also a possibility to discretize this using only one element. One element, then how do we take care of this P and M, because there is no node there? So how do we apply these, how do we take care of these forces P and M? So I will explain you how to do that. So for solving this problem, as I said, let me write that. So there are two ways of solving this problem. One is discretize the beam such a way that, discretize means divide it into number of elements. Discretize the beam such a way that nodes are there at the location of concentrated forces and moments. Nodes are there at the locations of concentrated forces. So that's the first way. Like for this example, I said you divide it into three elements so that you have nodes at these locations. So and the second is, no, rather than discretizing into it into say three elements, use a single element. Use a single element. Although no, the number of elements ultimately depend on the convergence study, so that one has to do. But as an exercise, I am just telling you that how to model this using a single element. Essentially, that is to say that how to include concentrated forces and moments at the any point in between the element. So use a single element and include. So the second approach is and include potential of in this case p. Potential of p will be p into v, basically minus p into v at x is equal to l dash. And potential of m, the potential of m will be basically minus m into uh, theta at x equal to l double dash. So that's the second thing. So the first is straightforward. We have already discussed problems, so you can do this. Now the boundary condition, of course, would be at the left in the deflection and slope both would be zero, but at the right end, that is at D, only deflection will be zero, slope would be non-zero. So if you are modeling it into three elements, you can solve the problem like that. So I'm going to discuss the second approach. So in case of second approach, then what happens to the integral functional within the element? So the strain energy part remains same, that is half of d transpose into ke into de. So this part basically same, and if there is a distributed force, external applied distributed force, so then there would be f external for the element, so that remains as it is. Now what you need to do is of course minus the internal force, so you will have d transpose into f internal for the element. Then in addition to this, what you are going to have is these terms, they contribute this term and this term, the potential of the concentrated force p and potential of the concentrated moment m. So now see this minus p into v at x is equal to l dash. So v is nothing but h into d. So then h has to be evaluated at x is equal to l dash, and of course we write it as v transpose into p. So v transpose would become d transpose into h transpose at x is equal to l dash. So then the contribution of this would become d transpose. So essentially this term is coming from this one, so you write this as minus b transpose into p, and b is d transpose into h transpose, and that is evaluated at x is equal to l. So you get here h into h transpose at x is equal to l dash into p, and minus, the last term is minus de transpose into then you have this m into theta. Theta is dv by dx, so you write it as basically minus m into dv by dx transpose, which can be written as d transpose into dh by dx. So that I'm denoting here as minus d transpose into dh by dx transpose evaluated at x is equal to l double dash into m. So this has to be actually included. So as I already explained that no, the quantities which I have used over here, the value of v at x is equal to l dash and theta at x is equal to l double dash, they come from this, that we know v of x is equal to this interpolation, Hermite interpolation functions h1 h2 h3 h4 into we have de, and then v at x is equal to l dash will be simply let me write it below there. So then V at x is equal to L dash will be basically this H1, H2, H3, H4 whole thing evaluated at x is equal to L dash into DE. So then its transpose is going to be D transpose into H evaluated at x equal to L dash. So you can say this as H eval trans yeah, simply I'm writing V, and of course when you take the transpose you have to write that. So this is at x is equal to L dash into DE. So its transpose is D transpose into H at x is equal to L dash. So that is what I have written over here. Now if you look at these two terms, this term and this term, and similarly if you look at the dV by dx, so theta is at x is equal to L double dash, which is nothing but actually dV by dx at x is equal to L double dash, the second location. So this is nothing but dH1 by dx, dH2 by dx, dH3 by dx, and dH4 by dx evaluated at x is equal to L double dash into dE. So the derivative of this H matrix I am writing as H dash. So H dash means it is derivative of the H matrix, the interpolation matrix evaluated at x is equal to L double dash into dE, and then its transpose would be D transpose into H dash at x is equal to no L double dash. So that is what I have written, as you see now, this term and this term. So it is coming from there. So this is how no, these are written. So finally now with the inclusion of no, these two terms, the potential of P and M, if you look at the finally the element level governing equation we will have is this part is same, Ke into De is equal to, if there is a distributed force then this F external will be there. This is due to distributed force per unit length in the element, plus F internal will be there, which is in terms of the shear force and bending moment at the end, plus you will have now these additional terms. So we will have this H transpose at x is equal to L dash into P, this term would be there, and plus you will have H dash transpose evaluated at x is equal to double L L double dash into M. So now you will have basically these two terms which will take care of the concentrated forces and moments within the element. So this is when we are solving the problem using a single element, and in between the two nodes, in the nodes of the element we have concentrated forces and moments. So this is the second way of solving this kind of problems, but usually of course the first approach is the one which is actually preferred. The first approach in the sense that you discretize the whole beam in such a way that there are nodes at the locations of concentrated forces and moments. So you discretize such a way that you have nodes so that you can take care of the concentrated forces and moments. But if you are asked to solve a problem in such a way that there is no node at the concentrated force or moment location, then you have to handle those forces and moments through these potentials. So you will see of course that these are going to contribute to because in general H and H dash, that is H and dH by dx, at the intermediate locations all the say functions are their derivatives would be non-zero. So this P will get then no distributed at the two end nodes of the element, and similarly the same. So this is how you solve this kind of problems using single element, that is without having node at a location where there are concentrated forces and moments. So the next is I also wanted to talk about this. We have developed the element level governing equations from a total potential energy functional or the integral functional. And suppose we don't want to do that, but we, so for any problem, even for the trust problems we have done, we can follow this approach. So and I'm also I want to discuss this element level governing equations using weak form. So directly how do we do that? So next is element label governing equations using weak form. So now the problem, we are taking the same problem, that is the same one element, we are considering one finite element. So with the local coordinate as capital X and Y, and the distributed force is transverse force per unit length, so that is Q. And the forces on the left and the right ends are the shear forces and bending moment. So this is S1E, and we have this M1E, and this side is a S2E, and a moment, that is M2E, and this force is Q. So these are the forces. So this is a beam. So you know already, know the governing equation we have derived. So why I am talking about governing equation, because we want to use directly the weak form. So first, you already know, any given differential equation, you need to have the governing differential equation, the governing equation of the problem derived from the physical principles. So this is d2 by dx square ei d2v by dx square minus q equal to 0. So this is the governing differential equation. Then we have weighted residual statement. We have discussed these concepts, I am just only writing this. So weighted residual statement is integration 0 to L, and wi is I am taking the weight function into the differential equation, d2 by dx square into ei into d2v by dx square minus q dx equal to 0. So this is the weighted residual statement. Then you also know we have derived the weak form. So the weak form is basically, I have derived, so I am just writing dy dx of ei into d2v by dx square. This whole thing is evaluated at 0 and L, minus dwi by dx into ei into d2v by dx square. Again, whole thing is evaluated at 0 and L. So because we do the integration by parts twice, so we get two boundary terms. So these are what we get. And then integral, we have 0 to L d2wi by dx square. So this will be the integral term, and the derivative of v and weight function w are same in this case. And minus, we have integral 0 to L wi q dx, and this whole thing is equal to 0. So this is the weak form of the weighted residual statement. And now if we say that I know the value of d by dx at x equal to 0 and L, 0 and L, and similarly the value of ei into d2v by dx square at 0 and L are shear forces and bending moments at the corresponding locations. So we can write this equation as, no if you look at the upper boundary, we will have wi into this term, and negative of this is denoted as shear force. So then we will have minus wi evaluated at x is equal to L into S2E, the shear force at the right end. And then we will have my plus wi evaluated at x equal to 0 into shear force S1E. And then we will have, similarly, this term has minus sign already, so minus dwi by dx evaluated at x is equal to L into m2e, and plus we will have dwi by dx evaluated at x equal to 0 into m1e. So yeah, these are the boundary terms. So two terms from this, two terms from this. So I have written them explicitly, and of course the other terms remain same, that is integral 0 to L and d2 wi by dx square into ei into d2 he by dx square dx, and minus integral 0 to L wi q dx equal to 0. So this remains as it is. So now here I know the same definition, so of shear force and bending moment. So we are in S1E, we are using for this minus d by dx of ei into d2 he by dx square at x is equal to this is at 0, and S2E the shear force at the right end of the element d by dx ei d2 he by dx square at x is equal to L, and similarly the bending moment at the left end m1 is ei into d2 he by dx square at x equal to 0, and m2e is ei d2 he by dx square at x is equal to L. So yeah, this is the big form and written in this manner. So we have explicitly written the bending moment and shear force in the in the boundary terms. So this is the weak form, and using this weak form, now we want to develop the element level governing equation. So we already know, we know that the same way, the way we have used the approximate solution for V. So those steps are same exactly the way we did earlier. So we will have this as h1, h2, h3, h4. These are the Hermite interpolation functions into dE. So we write that as h into dE, as you already know, and the d2v by dx square would be the second derivative of these say functions, dh1 by dx square, d2 h2 by dx square, d2 h3 by dx square, and d2 h4 by dx square into dE. D is the vector of elemental degrees of freedom, that so this we call as B into dE, and D is nothing but V1 theta 1, V2 theta 2, V3 theta 3. That's the same thing because we are talking about the same Euler-Bernoulli beam element. Now earlier we were using the integral functional, and now if we want to derive the element level governing equation directly using this weak form, so then for the element we have 4 degrees of freedom, V1 theta 1, V2 theta 2. So we should have 4 equations, and how do we get 4 equations? Is by choosing 4 different weight functions. So if we use Galerkin method, then in the Galerkin method the weight functions are same as the interpolation functions. So if we use Galerkin method, so as per the Galerkin method, we will choose the 4 basically the shape functions. So basically we would choose wi equal to hi. So now let us say w1 is equal to h1. So what equation do we get? That is one weight function is this. So now when you look at when w is h1, and we already know h1 is unity at node 1 and 0 at node 2. So if you look at in this weak form, this term would be 0 because w is h1 and h1 is 0 at x is equal to L. So this term would be 0, and we know that h1 is unity at node 1, so this would be non-zero. And then we also know that the derivative of h1 at x equal to L as well as at x equal to 0 are 0. So then in that case this term will also be 0 and this term will also be 0. So out of the 4 boundary term we will have contribution from only one, so that is going to be s1e, and then plus we will have integral 0 to L and w no second derivative of w1, which is dh1 by dx square into ei we have, and then second derivative, that is d2v by dx square, we are writing as b into de I am taking on the right hand side. So then we will have here this de, and minus integral 0 to L we will have h1 into q dx, this is equal to 0, and let us call this as equation number 1. So now similarly by take w2 equal to h2, in the Galerkin method we are taking the weight functions as the coefficient of unknowns in the approximate solution. Unknowns are v1 theta 1, v2 theta 2, so their coefficients are h1, h2, h3 and h4. So we are taking that. Now if you take w2 equal to h2, we know that h2 is 0 at node 1 and 2, so this term in that case will be 0, this term will also be 0, and h2 derivative at x is equal to l is 0, so this would be 0, only this term would be non-zero, because a derivative of h2 at x equal to 0 is equal to unity. So then from the four boundary terms, we will have only one, that is m1e plus integral 0 to L. Now w is h2, so we will have d2 h2 by dx square into ei into b into we will have dx into de minus integral 0 to L h2 q dx equal to 0. So let us say this is equation number 2. And then now you go for the w3, the third weight function will be h3. And now, as you know, as per the properties of this Hermite interpolation function, h3 is 0 at node 1 and unity at node 2, and its derivatives are 0 at both the nodes. So when we look at this term is going to be non-zero, because wi is h3 and h3 is unity at second node, so this term will be there and these terms will be basically 0. So now this case we will have the boundary term as minus s2 into e s2e and integral 0 to L d2 h3. Now the weight function is h3, so d2 h3 by dx square into ei into b dx, and then de minus integral 0 to L h3 q dx equal to 0. So this is equation number say 3. So then also we have w4 will be h4. So same way the arguments I discussed, this will be m2e plus integral 0 to L and d2 h4 by dx square into ei into b dx into d. So it's actually it's straightforward, minus integral 0 to L h4 q dx equal to 0. So this is equation 4. So now what you can do is, if we want to bring it in the same form, the way we got the element level governing equation from integral functional, so we can combine all the four equation 1 2 3 and 4 and write it in the final form. So if we combine these, so combining equations 1 to 4. So if we combine these equations, what do we get? So let us say these terms we want to keep on the left hand side and the remaining terms on the right hand side. So then I will have if I combine all these, so I these are four equations. So first equation, second equation, third equation, and fourth equation. So we want to put them in the in terms of rows. So then this would be integral 0 to L, and then this ei I can write it anywhere. And in each equation, on the first equation we have d2 h1 by dx square. Second equation we have d2 h2 by dx square. Third equation we have d2 h3 by dx square, and fourth equation we have d2 h4 by dx square. So this is one term we have, and then of course we have this b and dx. So all four equations can be actually combined in this manner, and then here you have this d, and then other terms I am taking to the right hand side. So we have integral 0 to L, and first row we have h1, second row h2, third equation h3, fourth equation h4. So we can put all of them together, h1 h2 h3 and h4, all of them together into q dx. So this is what we will have, and plus the other forces we have is minus s1e minus m1e s2e and m2e. So you can write actually these equations in this manner. Now in this, if you look at basically this term is nothing but actually B transpose. So as you know this, So now I can write this equation as integral 0 to L. I can say that EI into B transpose into B dx. So this is the stiffness matrix KE into DE. So we are exactly getting the same thing what we have got earlier is equal to integral 0 to L. We have H transpose into Q dx because this is nothing but H transpose. And then we have this plus internal force vector F internal for the element, this one. So this equation, the element level governing equation, is same as what we got from the integral functional. So you can get, no, if you have a differential equation whose integral functional exists, so then whether you use the integral functional or you use the the weak form, you will get the same element level governing equation. And this is more general because even for the problems for which integral functional doesn't exist, so that means problem doesn't involve even order derivatives, then also you will be able to, using the weak form, you would be able to develop the element level governing equations. So yeah, this is the additional thing I wanted to discuss. The application of this element is same. So now the next is, so far we have discussed, one is the the truss element for the load was along the axial direction, and we have now discussed the Euler-Bernoulli beam element in which the load is in the transverse direction perpendicular to the length of the beam. And now we could actually have many a times in, in the applications you will have the situation where the axial load is also there and a transverse load is also there. So for that kind of an element you have to have the axial displacement degrees of freedom, and also you have to have transverse displacement and the slope as degrees of freedom. So that kind of an element is known as frame element. So the next I am going to discuss is the frame element. So frame element, what I am saying, I just said that loading in both the directions are there. So that is loading in axial and transverse directions. So you have a situation of this type. Say for example, if I talk of a application, so the application would be the simple case you have let's say in a submarine you have some support for a piping or some other gadget, and the support for the piping or the gadget is anchored at two locations. So one location is anchored here. Of course at these ends there can be different boundary conditions, and one side, no, there's some sub piping is there which is exerting a distributed force. So you have this kind of a situation. So now in this situation you would see that because these two parts, this part and this part, they are connected and there is a transverse load. So no, at this location there is going to be bending moment and shear force. So it will try to exert an axial force on this, and also it will try to bend it. So axial deformation is there, bending is also there, and due to this there is going to be axial force in this, so it will bend as well as deform axially. So you have to handle this kind of a situation. So for this we have frame element in which we have both axial force and also the transverse force, and then the degrees of freedom are also having both the displacements along the axial direction and the transverse displacement and the slope. So now if I draw the element, and I am still talking about a two noded no element. So this is the element. The local coordinate system is, this is local x axis, and the local y axis is capital Y right now I'm using. And in the element there is a force along the x direction. This is the distributed force, let us say qx. Along x direction there is a distributed force, or there can be concentrated forces and moments along the y direction. So this I am calling as qy. Now since this is an element, so there would be some part on the left and right. So there are going to be now the shear force, bending moment and axial force. So the shear force here is going to be S1E, and the bending moment is going to be m1e. This is same as what we discussed earlier. Now addition to these there would be axial force, so let us say that is q1e. And similarly here you will have q2e, you will have shear force s2e, and you will have bending moment m2e. So these are kind of forces which are going to act. So there are axial, as you see here, the axial force, distributed force Qx is there. Qx is the force per unit length along the x direction. Qy is the force per unit length along y direction. And as the C axial force, shear force, bending moment, those are also there. So these are forces. If you talk of degrees of freedom in this element, so the degrees of freedom in the element are going to be now, we are talking of a two noded element, so node 1 and node 2. So this is node 1 and node 2. So the degrees of freedom are going to be now the axial displacement, that I am denoting as u naught 1 for the element, and there is going to be transverse displacement. So v1, I know the uh, transverse displacement at node 1. So you are going to have v1e, and there is a slope which we call as dv by dx at node 1 for the element, which we are denoting by theta 1e. So same thing at this node, you will have u naught 2 for the element, the degree of freedom is v2e, and you will have this theta 2e. So these are the degrees of freedom at the second node. So this is how no, this element would be. So ideally, without going into the detailed derivation, you could write the eliminable govern equation, because it's a combination of two noded truss element and two noded Euler-Bernoulli beam element. So you can ideally combine those two eliminable govern equations and write the govern equation for this frame element. But I just want to give you know the basics of that, how to develop the element from the basic considerations. So let me discuss that. So as we discussed earlier, so next we talk of the displacements. So our starting point is basically the displacement. So when I am talking of an element, so this is the element, this is the local x-axis, this is the local y-axis, and this is the undeformed configuration of the beam. And when it deforms, it takes a shape like this. So now it would also stretch axially. So now you see the length I have in the figure I have drawn, which is longer than, of course this is an exaggerated view. So if I take some point, say a point, no, a cross section here, this is a cross section, and this is at a distance y. This is a point, and this point is at a distance y from the central line y equal to 0 line. So then this line in the deformed beam actually goes somewhere here. So that line, ultimately, this particular line in the deformed configuration is going there. And if you look at this line, so it has rotated by an angle, and that rotation angle is dv by dx. So if I talk of now this point would have actually gone somewhere here. So now if you look at the displacements, so one is that the center point, that is, this was the center point. This center point has gone over here. So the displacement of the center point is we are denoting as u naught. So that this center point has got displaced by an amount u naught, and the rotation is dv by dx. So if I draw a horizontal line over here and a tangent at this location, so this angle is also going to be dv by dx. So if you just look at this, is the additional displacement. So if you look at this displacement, it's actually going to be y into dv by dx. So if you look at the displacement along x direction, uxy, uxy means the displacement of any point of the beam at a location x, and the y will be given by. So for now we are writing the displacement for this point. So to write the displacement of that point, it has the center point itself. Now if you look at this center point, it has gone here. So along the axial direction, it has got displaced by an amount u naught, and u naught is a function of x. And then the finally this point, has got displaced, an incremental displacement along the negative x direction. So minus y into dv by dx. So that this is the displacement along the x direction. So this is the axial displacement. So earlier, if you remember, this term was 0. When we started with the Euler-Bernoulli beam element, this term was 0. We only had basically this term. But now since there is an axial load in the beam, so this term is also going to be non-zero. No, Euler-Bernoulli beam theory, U naught was 0 everywhere, but now here it is going to be 0. And another displacement is V, which is the transverse displacement, and that we are assuming to be function of only x. So whether we measure the transverse displacement along the y direction, whether at top, bottom, center, or anywhere, it is same. And this is nothing but transverse displacement. Transverse means along the thickness, transverse displacement. So now if you look at the strain, so only non-zero strain is going to be epsilon xx. So I'm not writing the other component. Epsilon xx is, as per the strain displacement relation, it is del u by del x, and del u by del x y, because this u is a function of x and y, and since the derivative is with respect to x, I'm writing del u by del x, and this would be equal to du naught by dx, because we are putting this u as u naught minus y into dv by dx, and minus y, and then one more derivative, so d2v by dx square. So this is what is going to be strain, and the stress sigma xx is going to be E into epsilon xx, so that would be E into du naught by dx minus this y is capital Y. So I'm sorry, let me correct that. So capital Y I'm using. No, the local y coordinate is capital Y now over here. So this is capital Y minus y into d2v by dx square. So this is the stress, and only non-zero component of stress is the sigma xx. So now if you look at, for this case, if you look at the total potential energy functional or the integral functional, so which will again consist of strain energy, potential of the distributed forces, and the potential of the concentrated forces. So total potential, yeah, so if you look at the total potential energy functional, or the integral functional, so I will be, first part would be half of that is the strain energy, so which is half integration over volume. Integration over volume is split as integration over length 0 to L, and integration over the cross sectional area, and then it is sigma xx into epsilon xx, and sigma xx is E times epsilon xx, and epsilon xx is given by, actually this expression. So ultimately you can write this part as E into du naught by dx minus y into d2v by dx square whole square dA dx. So this is the strain energy part. And then the potential or distributed force, so we have two distributed forces, force along the x direction, so its potential is going to be, work done is going to be positive, potential is negative, so u naught qx dx minus integral 0 to L, and then we have now this v into qy dx is the potential or distributed force qy, and then we have the potential of these forces and moments acting at the left node, and forces and moments acting at the right node. These are internal forces. Why I'm saying them internal? Because they are coming from the country, due to the the elements adjacent to that element, left side and right side. So this is similar what we wrote earlier, that in terms of degrees of freedom, u naught 1 for the element, then we have v1 e, then we have theta 1 e, then u naught 2 e, v2 e, and theta 2 e. So these degrees of freedom transpose into all the internal forces. So we have minus q1 e, then we have s1 e, minus S1E minus M1E, that is these are the axial force, shear force and bending moment on the left side of the element, and then axial force, shear force and bending moment at the right end of the element. So this is what is going to be the total potential energy functional. And in this, if you look at now the now let's look at the no the first term. These things are straightforward. So the way we write, I'm finally going to of course combine. So but let me just talk of the strain energy part. So if you look at the strain energy part only, so integral half integral 0 to L integration over the cross sectional area is the Young's modulus. And if you expand this, open this square, so then you will get du naught by dx whole square plus y square into d2v by dx square whole square, and minus 2 into y into du naught by dx into d2v by dx square. So this is what you will get, the this term. So you have of course this dx, and then the other term, this term they remain as it is. So we'll have minus rest of the other terms. I'm not rewriting them again. So now only I wanted to discuss if the beam cross section is such, if the beam cross section is symmetric about y equal to 0 plane. So I know if you look at the coordinates we have taken, so this is x and this is y, this is the y equal to 0 surface. So if the beam cross section is such that it is symmetric about this plane, this plane, so that is this side and this side, the beam cross section is identical, then the integral y dA would actually be 0. So no, that means finally this term will not contribute to the strain energy term. And of course, if the cross section is not symmetric about y equal to 0, then you also have to take this term. So for symmetric cross section about y equal to 0, I'm saying y equal to 0 plane, we will have this integral y dA will be actually equal to 0. So that means this term is going to be 0. So therefore, you would be able to say that this I is going to be half integral 0 to L, and then this term is does not involve any cross sectional coordinates, so it would be integral EDA. This is only function of x, so integral EDA will give you simply area. So we will have E, and then this term would be A. Now I'm performing the cross sectional integration, so that will simply give you A. So we will have du naught by dx whole square, this term would be there. And then the second term is y square dA. Y square dA is izz, which be denoted as I. So the second term would be I into d2v by dx square whole square, and then dx. And the other terms, as I already said, no, this term is 0, integral y dA is 0, so this term doesn't appear. And then minus, of course, we will have the remaining terms. So finally, what we can do is we want to write this as a product of matrices and vectors. So we can write this as half integral 0 to L, and then see I want to write, I want to take this vector as see this du naught by dx and d2v by dx square as one vector. So we will have transpose of this, and at the center now I have this ea, then 0 0, and this ei, and then this side the same thing, du naught by dx and d2v by dx square dx. So now if you write it like this, ultimately if you multiply this term and this term, you are going to get basically these. So the two are one and the same thing. Only thing is now this is a 2 by 2 matrix, and you see this vector is a 2 by 1 vector, and its transpose would become 1 by 2. So ultimately the whole thing is a scalar quantity. And then also I want to write these two terms of the potential energy, that is these two, we can combine them together. Now this term and this term, combine them together. So when you combine, so you can write that term as minus integral 0 to L, and then we have u naught and v transpose into qx qy. So again, if you multiply u naught v transpose with qx qy, you are going to get the same thing what we have written over there. So this will be there, and minus, of course, we have that the contribution of the internal forces. So d transpose and into f internal, where no this d is basically this vector is your de, and this one we are denoting as f internal for the element. So you can ultimately write the integral functional. The first, this part is the strain energy part, and this is the potential of distributed forces qx and qy, and this is the potential of internal forces. So you can write it like this. Now once we have this, so now there are two variables. You see u naught and v. No, they no. So there are variables u naught and v, and both have to be interpolated. So the approximate solution, and also it is similar to what we discussed for the truss and beam, Euler-Bernoulli beam elements. So now if you look at the interpolation for each of these variables, so the element is a two-noded element. Two-noded element, and I have already talked about what are the degrees of freedom. So this is capital X and this is Y. The degrees of freedom I have already talked about, that what are the degrees of freedom for this element now in this diagram. So these are the degrees of freedom, whatever is given over there. So now the interpolation, if you look at, so now if you look at this integral functional, so highest order derivative of u naught is first derivative. So it should be and the corresponding primary variable is going to be only u naught. So at 2, that means at the in nodes 1 and 2, u naught should be there as degrees of freedom. So for the element as a whole, there would be 2 degrees of freedom, u naught 1 and u naught 2. And so therefore we can take a linear polynomial. U naught can be taken as a naught plus a1x, and when you express a naught and a1 in terms of u naught 1 and u naught 2, you get the interpolation for u naught as this n1 into u naught 1 for the element plus n2 into u naught 2 for the element. So where the shape functions are the same shape functions, so now we have defined earlier. So n1 is 1 minus x by l, and n2 is x by l. We have defined this. So these are the same shape function we used earlier. And if you look at v, highest order derivative of v in the integral functional is second derivative, and corresponding primary variables are d and dv by dx. So at the in nodes, that is node 1 and node 2, we will have corresponding to v, the degrees of freedom would be v and dv by dx. So 4 elemental degrees of freedom, therefore 4 terms in the approximate solution. And when those unknown constants, say b0, b1, b2, b3, are expressed in terms of values of v and dv by dx at nodes, we get the interpolation of v in terms of Hermite interpolation function. So v would be equal to h1 into v1e plus h2 into theta 1e plus h3 into v2e plus h4 into theta 2e. So this is same actually. For the truss element we use this. For the Euler-Bernoulli beam element we have used this. Now we are going to use both of them simultaneously, because now the element at hand has got both the degrees of freedom. So the shape functions are already defined, so I'm not writing them again. N1 is 1 minus x by l, N2 is x by l, and h1, h2, h3, h4 are Hermite interpolation functions which we have defined earlier. So now if you write this in the form of matrix and vector, so now you will get this u naught and v naught. There are two variables. So I will know if I want to write this as product of matrices and the vector of elemental degrees of freedom. So vector of elemental degrees of freedom is u naught 1, v1e, theta 1e, u naught 2e, v2e, and theta 2e. So this is the vector of elemental degrees of freedom. And all of them are primary variables, and they are the degrees of freedom at the in nodes of the element. So now u naught is written as n1 into u naught 1 plus n2 into u naught 2. So and see, u naught 1 is at location 1 and u naught 2 is at location 4. So we should have n1 there, and then 0 0, because no v1 and theta 1 are not contributing to u naught, and then n2, and again 0 0, because v2 and theta 2 are not contributing to the interpolation of u naught. And then in v we have h1 h2 h3 h4. So we will have no 0, then h1 into v1 plus h2 into theta 2, and then again 0 here because u2 u naught 2 is not contributing to v. Then we will have h3 and h4. So this is how your interpolation matrix would be. So this is u naught into v, no u naught and v equal to, this is the interpolation matrix h into de. So that is what I was mentioning, no, that interpolation matrix would be, no, in general a matrix. No, of course, the earlier two elements, it was a vector, actually a row vector, but now you see this is a rectangular matrix. So this is 2 by 6 matrix, and this is a 6 by 1 vector. So same way, no, we need in the integral functional the derivatives of u naught and v. So we require du naught by dx and d2v by dx square. So these also can be written in terms of the derivatives of the shape functions. So and the vector of no degrees of freedom. So that is, no, we are calling no, this is de. So now let me write just here just de. So du naught by dx is dn1 by dx. So in the matrix we will have dn1 by dx 0 0, dn2 by dx, and then again 0 0, and then d2v by dx square would be in terms of these derivatives, h3 and h4. So now we will have 0, and then d2 h1 by dx square, d2 h2 by dx square, then 0, d2 h3 by dx square, and d2 h4 by dx square. So yeah, this is the, now we call this as no, strain displacement matrix. So we put here b and into de. So b is this, and this you see here it is a 2 by 6 and this is 6 by 1. So now what you need to do once you have got these u naught and v equal to h into d, this equation, and du by naught by dx and d2v by dx square is equal to this. So you substitute this in the integral functional, that is this functional over here, and no, then take delta I, no, from delta I equal to 0 with delta d as arbitrary, you get the element level governing equations. So those steps are basically the same the way we have discussed earlier. So let me write directly the element level governing equation. So then you can say here that element level, now we are talking of a frame element. So frame finite element. So element level governing equations. So that is going to be same form of the equation is same, k into d, the element level stiffness matrix, is equal to f external for the element plus f internal. So this is same. Only thing is we have to define what are no, the k, f external, f internal, and d we have already defined. So you will see that in this case ke will be basically integral 0 to L, and then we will have now B transpose, and this is a 2 by 1 matrix. We have EA 0 0 and EI, so this is a 2 by 2 matrix in between B into dx. So this is what is your ke. You will see this is a 2 by 2 matrix, B is a 2 by 6 matrix, and B transpose would be 6 by 2. So ultimately this is going to be 6 by 6 matrix. So you will see that now the stiffness matrix is of size 6 by 6. And if you look at the external loads, F external for the element, so this is going to be integral 0 to L. Now we have H transpose, and then this Qx and Qy dx. So as you know, H is 2 by 6 is its transpose is going to be 6 by 2 into 2 by 1. So ultimately this would be a basically a 6 by 1 vector, no, the external load vector, due to distributed forces along x direction qx and distributed force along y direction qy. And if you look at the f internal for this element, so no, let me write its transpose so that I can write it in one row. So AF internal transpose will be minus Q1E minus S1E minus M1E, then Q2E, S2E, and M2E. It's actually, so F internal is a column vector, its transpose would be a row vector. So that is what I have written. Now let's look at the know the uh, finally the stiffness matrix K and the load vector F external. If EI, QX, and QI are constant within the element. So let's look at that. So for, as we have been doing earlier, so we want to solve problems. For that we need the explicit expression for the Ke and F external. So let us say EA, EI, QX, and QY are constant for EA, EI, QX, and QY constant within the element. Although finite element can handle the variable situation also. So for that, let's now I'm going to directly write. So actually what you are going to do is now you have to put here. So I'm skipping all those steps. You now have defined B, so you have to multiply all these three matrices and then carry out the integration each term there in this 6 by 6 matrix. So what you will actually get is the combination of stiffness matrices for the truss and beam. Now this, for this case, you will find that this element level stiffness matrix Ke, when EI and EI are constant and the element length is L. So you will find that this will come out as, you will find that this matrix is going to be, of course, is a 6 by 6 matrix. And you will find actually the degrees of freedom are, first degree of freedom is displacement along x direction, second is transverse displacement along y, third is the rotation, and then fifth, sixth, and seventh are the displacement along x, along y, and rotations at the second node. So you will find that the first and fourth degree of freedom are corresponding to displacement along x direction. So then the first and fourth rows and columns of the stiffness matrix would correspond to the stiffness of the truss element we have discussed already. So you will find when you multiply B transpose and then 2 by 2 matrix at the center and then again B and integrate. So you will get here EA by L, you will get 0 0, then you will get minus EA by L and 0 0. So this is what you will have. The second row, this term would be 0, and this would be what we got for the stiffness matrix of the Euler-Bernoulli beam element. So 12 EI by L cube, and then we will have 6 EI by L square, and then here we will have 0, and then minus 12 EI by L cube, and 6 EI by L square. So this is the second row. The third row would be 0, and then we will have 6 EI by L square, 4 EI by L. Now I cannot take no EA or EI common, so I am keeping them inside. Otherwise, it is same as the stiffness matrices for truss and Euler-Bernoulli beam element. So minus 6 EI by L square, and then we have 2 EI by L. So you will see that this is nothing but the stiffness matrix of the actually Euler-Bernoulli beam element. And then here, now this is the fourth row. In the fourth row, we will have stiffness term of the truss element. So minus EA by L, 0 0, and this is a diagonal element. So EA by L, and again 0 0. And then the fifth row will be corresponding to Euler-Bernoulli beam degrees of freedom, that is V and theta. So we will have minus 12 EI by L cube, minus 6 EI by L square, 0, and then 12 EI by L cube, and minus 6 EI by L square. And then the last row would be 0, and then 6. Of course the matrix is symmetric, so no you can always write only half of it, 0, and minus 6 EI by L square and 4 EI by L. So this is what is going to be the, so for solving problems, you know, with constant EA and EI within the element, you can directly use this stiffness matrix for the frame element. Now the F external for no, this element will be, so we have already said it is integral 0 to L H transpose into Qx Qy dx. And if you carry out now, the Qx and Qy are constant within the elements, so if you carry out this integration, you will find that this would be Qx L by 2, then Qy L by 2, and Qy L square by 12, and then again Qx L by 2, Qy L by 2, and minus Qy L square by 12. So you will see that these terms are coming from the truss and these are coming from the Euler-Bernoulli. So this is same, and what we know is just the combination of what we have already discussed. And now if you look at the internal load vector, so F internal for the element, F internal is of course the same what we have already discussed, minus Q1E minus S1E minus M1E, axial force, shear force, bending moment at first node, axial force, shear force and bending moment at second node. So this is the internal load vector. So with this is what you have, and now the assembly procedure, assembly, the imposition of boundary condition and solution is similar what we have discussed no, earlier. So the solution involving this element are also going to be actually similar. So before now, of course, you can directly also solve some problems, but in general, when you are talking of frames, so, what is the difference between a frame and a truss is that in a truss, the joints, the members are connected through a pin joint. So, there are no rotational constraints. But in case of frames, the members are connected rigidly either through the welding or whatever. And therefore, there are no rotational constraints at the joints. So, then we have to use the what is known as the frame element. Now, when you use a frame element, you will encounter one situation that all members, again similar to truss structure, will not be oriented in a same direction and a single direction. The members would be in different directions. So before we can assemble the elements, we need to transform the element level governing equation into a common coordinate system. So we need a transformation. So we call as a 2D transformation for frame element. So that means 2D, that means 2D frame structure. 2D frame structure means all the members of the structure are in a one plane. So let me discuss the 2D transformation for frame element. For frame element, so I think let me for frame element. So yeah, I think I hope I. Hello. Yeah. So, am I audible? I think yeah. No. If you ask questions in between, so then I'm sure that you are able to listen to me. But I think if people don't ask any question, although I always keep telling that no, you can stop me and ask questions. So hello, am I audible?
Yes, sir.
Okay. So now what I'm saying is that when you take the structure, now the members are oriented in a different directions. So let me take a simple example. And this complexity you would see, whether if you look at the arrangement of stringers and rings, either in a ship or submarine, these are the most common examples I'm taking so that if you would have seen in a dockyard how these ships and submarines are constructed, so you can actually appreciate what kind of complex stiffeners structure is there in the orientation of these members. So now let me take a simple example why there is a need for transformation. हेलो मेरी क्लास चल रही है So now see, you have this one member is in this direction, but the another member is now in this direction, and there can be of course any boundary condition. No, I'm not very specific to any one kind of a boundary condition, but there can be any boundary condition. Let us say this is on a pin support and this side is fixed. So now when we, and there could be different distributed loads or concentrated forces and moments. So now if you look at the local coordinate system for this element, so this would be capital X and this would be capital Y. And if we take the global coordinate direction in this itself, so this would be global coordinate small x and global coordinate small y. But for the second member, no, the element, now this will be the local element is x-axis is going to be along length of the member, so the local element x-axis is going to be this, and the local y-axis is going to be this. The global coordinate axes would still be the same, this as x and this as y, so this would be at, say, at some angle alpha. So before we can assemble these two elements, let us say this is element 1 and this is element 2, and the nodes are, although you can discretize each using a number of elements, global node number 1, global node number 2, and global node number 3. So before we can assemble these elements, we have to transform the element level governing equation into a common coordinate system, as we discussed earlier. So here, if you look at this small xy, these are the global coordinates axes. So these are global coordinate axes, and capital X and Y are local coordinate axes. So as we did for the truss element, same kind of a transformation we have to use here. Only difference is that earlier we had in the local coordinate system only the displacement along the length as a degree of freedom, but now we have displacement along length and also displacement along transverse to the element length as the degrees of freedom and the rotational degree of freedom. So let me say that when we are talking of an element which is at certain angle with respect to the global coordinate axes. So basically, this is the element, this is the local x-axis, any element, and this is the local y-axis, and the global coordinate axes are small x and y. This angle is alpha. So now if you look at the degrees of freedom, so at this node the degrees of freedom are, in terms of the local coordinate system, the degrees of freedom are u01, v1 for the element. So this is u01e, v1e, and theta 1e, and at this node the degrees of freedom are u02e, v2e, and theta 2e. So these are the degrees of freedom in terms of components along the local coordinate axes, capital X and capital Y. Now the same thing if we look at the degrees of freedom in terms of the uh, global coordinate axes. So the coordinate axes are same, this is x and this is y. So the degrees of freedom are going to be along this direction, we will have u1e, and along y we will have this v1e in this direction, and then we will have rotation is same theta 1e. So similarly at the second node we will have u2e, this will be v2e, and then theta 2e. So what we want is, we want to write this small u small v in terms of capital U and V. So if you look at u naught and this u naught and v, these are the displacements along local x and y, and if you look at u and v, these are the displacements along global x and y. So that's the difference. Now how do we write that these degrees of freedom in terms of the local coordinate axes, in terms of the degrees of freedom in terms of the global coordinate axis? So for that if you, let's say, take node 1, so for node 1 we have u1 e, and we have this v1e in the global coordinate system. In the local coordinate system we have u01e, and we have this v1e, and this angle is alpha. So you would be able to write that you can say that u01e, that is this displacement. You take the component of this capital u1e in this direction, and you take the component of v1, capital v1e along the x direction. So this would be u1e cos alpha plus v1e sin alpha. And similarly, when you write v1e, this, so you have to take the component of this along this direction, and you have to take the component of this along this direction. So you will find this v1e would be equal to minus u1e sin alpha plus v1e cos alpha. And same thing for the second node. So now if you put both these together, you can write the basically the the transformation matrix. So I think I have to stop here, and like I think, yeah, so I will stop here and discuss few more things. Yes, or should I come? Yeah, it's already, so I think let me stop over here, and then so try solving some problems. So I will give you some problems. So no, I think let me just give one problem. So the other problems I would give later. So try solving this problem. You should attempt. I'm not going to do it. So let us say that you have a beam, and at both the ends this beam is fixed, and the length of the beam is small 2l. So this is the length of the beam, and there is a distributed force in this direction. So this force is q, but at the center there is this beam is connected to another rod. So this is the rod here, it is connected to this point through a pin joint. This joint is a pin joint, and this side, this rod of course is connected, is also pinned. So that rod is pinned over here, and let us say that this point is B, this is C, this point is D, and this point is E, and the flexural rigidity is EI throughout the beam, and the load I have already discussed. And similarly for this, the length is this length is also L, this length, and the product of cross sectional area and Young's modulus is EA. So now try solving this problem. So what I suggest is that you discretize this using beam, you discretize using two Euler-Bernoulli beam element. So this will be global node number 1, this would be global node number 2, this would be global node number 3, and element number 1, element number 2, this would be element number 2, and this is the element number actually 3, and the global node number here is 1 2 3. So this is the node number 4. So while solving this problem, if you look at element 1 and 2 would be Euler-Bernoulli beam finite element. So when you model this using Euler-Bernoulli. So now for this you don't have to use the basically frame element. You can use the Euler-Bernoulli and truss element. So element 1 and 2, these two elements you model using Euler-Bernoulli beam finite element. So at each node 2 degree of freedom, b and dv by dx, that is theta. And element number 3, that is this element, this rod is the beam. If you look at the beam BCD is subjected to transverse load, whereas the rod this EC is only subjected to axial load. but there is no distributed force in between. But it is due to C, that there is going to be force from beam onto the rod EC, and that would be an axial force. So this can be modeled using two noded truss element. So you model this using truss finite element. And then the degrees of freedom are, the boundary conditions are at B, no, at B V and theta are 0, at D, that is node 3, V and theta are 0, at C of course you will have some non-zero V and theta, and then you will also have, of course, at C you have to have the degree of freedom as UV and theta, and at E, that is node number 4, you have only U degree of freedom, and that is equal to 0 from the boundary condition. So you try solving basically this problem, and you could expect something similar in the minor, so you should try solving this. I'm not going to give you the solution. There is no, you have to work on your, I have given you the a hint that how to do it. So before, of course, imposition of the boundary condition, when you are assembling, so the as far as the degrees of freedom are concerned, as I said, at node 1 you have V and theta, node 2 U V and theta, and at node 3 V and theta, and at node 4 you have only U degree of freedom. So you try solving this. So yeah, I think this is where I want to stop. And now about the minor. So minor is going to be on 17th of February, and it is going to be exam in classroom. So it is not going to be online, but it is offline in classroom. And the for the exam, the classroom, actually I had written to timetable, central timetable in chart. So the room allotted is 602, but you can check in the the exam schedule. So the room number is LH 602. So in the lecture hall complex, it is the room number 602, LH 602. I will also send an email. So 17th, the timing. So the exam would be, because it is I will be distributing question paper and also the answer sheets. So you will be writing the answers in the answer sheet itself. So there is no online submission and anything involved. So you don't have to bring in your laptop and things like that. Of course, you need to bring in calculators and pen, pencil, whatever you need for writing. So you should bring that. The exam would be, timing would be, it is going to be 1.5 hours exam, because there is only one minor, so I want to keep it for 1.5 hours. So we will start from 8:20 and will continue till 9:50. So it would be from 8:20 to 9:50, and another 5 minutes for collecting the answer sheet. So we should close by no free no leave the room 60 LH 602 by 10. So that is as per the timetable. So that is what is about the exam. So I think, yeah, this is what I wanted to. And another thing I wanted to mention you, that I am very unhappy with the way you have done your assignments. So most of you have actually copied from each other. That is what was not expected, and there is going to be penalty for that, because you have copied. You are supposed to do on your own, not copying from others. And see, how do we get the infer about your copying, because same kind of mistakes, so and same kind of missing steps, and how you can get the next answer without the intermediary steps and things like that. So no, that is not what is expected, and there is going to be penalty for that. No, if you are caught copying, you found that you have copied, so there is going to be penalty for that. So yeah, with this I think I want to stop. If you have any doubts and questions, yeah, you can ask. Yeah, anybody want to ask anything related to whatever we have discussed so far, whatever I have taught so far? You can ask questions on that. You can ask question about minor. You can ask question about assignment, or anything you want to ask, you can ask.
Sir, in minor exam, good morning, sir.
Yeah,
Sir, in minor exam, till today's lecture it will be covered, no, sir?
yeah, it will till today's lecture. So whatever we have covered so far, it would be part of minor.
Okay, sir. Okay, it will be mostly numerical based, or MCQ also will be there, sir, in the paper.
No, there would be no MCQs. It would be, the most of it would be some derivations, solution of problems, derivation of weak form, integral functional, use of better residual methods for solving problems, use of finite elements for solving problems, development of the element level governance. So whatever we have discussed so far will be, the question paper is going to be based on that. So there would be no MCQ kind of questions. Yeah.
Okay, sir. Thank you.
Excuse me, sir.
Yeah.
So may I know, do we have to like by heart these equations and matrices, or it will be provided in the question paper?
I think your voice is not audible, so I didn't get what you were trying to say. So if I request you to write in the chat box if you know there is a problem. So you're, I think you were saying something about the question
Sir, am I
paper.
audible, sir?
Yeah, you are audible. Yes.
Yes, sir. I was asking whether like we need to by heart all the equations and all these formulas, or something will be provided in the question paper,
Yeah,
sir.
I think
Exactly what kind of approach
no.
we should be
I
having
think
towards the
so.
exam.
If that's the concern, so let me make it open notes examination. So you can bring in your notes.
Yes, sir. Understood, sir. So notes are allowed, sir, not textbooks.
Notes would be allowed, not books. So your no, you can bring in your notes in the exam hall. So all the formula and stiffness matrix and things like that, whatever you need, you can actually take it from the your notes.
Yes, sir. Understood, sir. Thank you, sir.
Yeah. So any other question, doubt? Anybody want to ask anything? Okay, then I'm stopping. Thank you all for your attention. Thank you. Wish you all the best for your minor.